Imagine living in a world where everything is perfectly predictable. A world where if you drop a ball, you know exactly where it will land, when it will land, and even how satisfying the bounce will sound. This was the dream of early scientists and mathematicians. For a long time, math was seen as the ultimate rulebook of the universe. It was neat, it was tidy, it was like a cosmic IKEA manual, except you didn't lose the screws. The big hero of this story is, of course, Sir Isaac Newton. You've probably heard of him, the guy who got hit by an apple. Or maybe he didn't. Nobody really knows if the apple story is true, but it's too good not to repeat. Either way, Newton gave us something much bigger than fruit bruises. He gave us the laws of motion and gravity. And with those laws, it suddenly looked like the entire universe was one giant clock. This clockwork universe idea became super popular. Think about it. If you know the position of every single planet, star, and particle, and you know all the laws of physics, then in theory you can predict everything that will ever happen. You could predict the next solar eclipse, the path of a comet, maybe even the exact time you'll stub your toe on the corner of the bed. Newton's equations gave people the feeling that the universe was completely under control. French mathematician Pierre-Simon Laplace pushed this idea to the extreme. He imagined a kind of superintelligence, sometimes called Laplace's demon. Don't worry, it's not as scary as it sounds. The idea was that if this demon could know the exact state of the universe at one single moment, the position and velocity of every atom, then it could calculate the entire past and future. Every sneeze, every stock market crash, every bad haircut, all written in the math. The universe was one gigantic domino chain, falling in perfect order. This was the golden age of determinism. Everything could be calculated, if only you had a big enough brain and enough paper. And people loved it, because it made the world feel safe. No surprises, no chaos, just pure cosmic order. Now, here's where it gets funny. People got a little too confident. They thought math could explain literally everything. Some Victorian scientists even tried to write equations for human behavior. Spoiler, that didn't work out. Imagine trying to predict whether your neighbor is going to buy a goat next Tuesday. Good luck with that. But the dream was there. If math could predict the motion of planets, why not the chaos of human life? Of course, even before chaos theory was officially discovered, there were cracks in this perfect picture. Let's take the solar system itself. Newton's equations could predict how two bodies, say the Earth and the Sun, pull on each other with absolute precision. But what about three bodies? Let's say Earth, Sun, and Moon. That's when things started getting messy. This became the famous three-body problem. You'd think adding just one more object wouldn't be a big deal. But the math exploded into insanity. It was like trying to juggle three chainsaws. And mathematicians realized something uncomfortable. Even with perfect equations, the system could behave in unpredictable ways. Henri Poincaré, a French genius from the 19th century, was one of the first to really dig into this. He found that small changes in the starting conditions of a three-body problem could lead to wildly different outcomes. Sound familiar? That's basically chaos theory hiding in plain sight. But back then, people weren't ready to embrace it. They shrugged and said, "Hey, too complicated. Let's focus on the things we can actually calculate without losing our minds." So for a while, the idea of perfect order still ruled. Mathematicians and scientists went around bragging about their predictive powers. They loved to show off by forecasting solar eclipses centuries in advance. And to be fair, that is impressive. Imagine being in the 1800s and someone telling you the exact date of an eclipse in 1999. That's like the ultimate flex. But beneath the surface, there was this growing suspicion. Maybe the universe wasn't quite as tidy as Newton's equation suggested. Maybe there were limits to prediction. Maybe nature wasn't a clock after all, but something more like a toddler. Unpredictable, messy, prone to throwing things at your head just when you least expect it. Still, in the centuries leading up to Lorenz and the butterfly effect, the official vibe in science was order rules, chaos rules. If you were a young mathematician in the 1800s, chaos was not the hot topic. Equations that made sense, those were the ticket to fame. Order was fashionable. Chaos was like that weird cousin everyone avoids at family dinners. And yet, little hints of chaos kept sneaking in. Weather, for example, was notorious. People had tried to predict it for centuries. Farmers depended on it. Sailors prayed about it. And kings occasionally lost wars because of it. But the weather refused to behave like a neat equation. Early meteorologists tried. Oh, they tried. They drew charts, measured winds, tracked clouds, but the forecasts were often hilariously wrong. Imagine telling the king, "Don't worry, tomorrow will be sunny," and then waking up to a blizzard. Not great for job security. The funny thing is, people still trusted math to fix it eventually. They thought, once we get better instruments and better equations, we'll nail it. Someday we'll be able to predict the weather weeks in advance, no problem. If only they knew what was coming. Because here's the twist. The problem wasn't just bad data. The problem was deeper. The problem was that nature itself had this hidden unpredictability baked in. A butterfly could flap its wings and change the outcome of a storm thousands of miles away. But we'll get to that soon. For now, let's pause and appreciate this moment in history. The world before chaos was a confident world. Scientists believed they were on the verge of a complete mathematical description of reality. They thought they were writing the final chapters of the universe's instruction manual. And then, as always, nature laughed, because the universe doesn't like to be told what to do. It doesn't follow our neat little rules forever. Sometimes it throws in a butterfly, just to keep us humble. So the stage is set. We've got Newton's clockwork universe ticking away, Laplace's demons smugly calculating every future sneeze, and scientists dreaming of predicting everything from eclipses to your bad haircut. They thought math had conquered chaos, but little did they know, chaos was about to make a grand entrance. Imagine you're living in the 1800s. Life is rough, but it's also kind of exciting. You don't have Netflix, you don't have Wi-Fi, you don't even have reliable plumbing in most places. But what you do have is a burning curiosity about the world, and one of the biggest mysteries of all time, the weather. The weather was basically nature's way of trolling humanity. Farmers needed to know when to plant crops. Sailors needed to know if they were about to be swallowed by a storm, and armies needed to know if they were going to march into sunshine or straight into a mud bath. But the sky didn't like to give away its secrets. Now, humans have always tried to predict the weather. The ancient Babylonians watched the clouds and made guesses based on patterns. The Greeks, being Greeks of course, wrote entire books about it. Aristotle even wrote a whole treatise called Meteorologica. But let's be honest, most of it was wrong. He didn't have satellites, he didn't have Doppler radar, he had a beard, a robe, and some guesses. By the 1800s though, science was feeling cocky. Remember, this was the age when Newton's laws made people believe the universe was a giant clock. Everything looked predictable, so naturally scientists thought, hey, if we can calculate the orbits of planets hundreds of years into the future, surely we can predict if it's going to rain tomorrow. Cue the birth of early meteorology. People started collecting weather data obsessively. They measured temperature, wind speed, humidity, barometric pressure. They drew beautiful charts, almost like works of art, full of swirls and arrows. And they were confident, very confident. Give us enough data, they said, and soon we'll be able to predict storms, hurricanes, even droughts with pinpoint accuracy. Spoiler, they couldn't. One of the most famous weather pioneers was an officer in the British Navy named Francis Beaufort. You might not know his face, but you know his work. He invented the Beaufort scale, which measures wind speed. You know those dramatic storm reports where they say, winds reaching category 10. That's basically Beaufort's legacy. He tried to bring order to the chaos of the sea, and to some degree he succeeded, but predicting when those winds would show up, that was still a nightmare. Then came Admiral Robert Fitzroy, another big character. Fitzroy is best known for captaining the HMS Beagle, the ship that carried Charles Darwin on his famous voyage. Poor Fitzroy had the unenviable job of babysitting Darwin while he collected beetles and stared at turtles. But after that, Fitzroy devoted himself to weather prediction. He invented the first storm warning system for ships, basically the ancestor of the modern weather forecast. And here's the cool part. Fitzroy was also the first person to use the word forecast in this way. Before him, people just said prediction. He thought forecast sounded fancier and less like fortune-telling. Fitzroy set up a network of weather stations across Britain, collecting telegraph data and trying to map out storms in real time. It was groundbreaking. Suddenly, you could send a message from one part of the country to another saying, hey, there's a storm headed your way. For the first time in history, people had something resembling a national weather service. But here's the problem. Fitzroy's forecasts were often hilariously wrong. Imagine opening the paper reading tomorrow clear skies and sunshine, and then finding yourself drenched in rain an hour later. People made fun of him mercilessly. Newspapers called his forecasts Fitzroy's lies. His work was so unappreciated that he became depressed, and tragically he eventually took his own life. Today, though, meteorologists see him as a pioneer, someone who tried to bring order to a system that would later be proven to be chaotic at its very core. It wasn't just Britain either. Across Europe and America, scientists were obsessed with weather maps. They thought if they just collected enough numbers, they could crack the code. In France, Urbain Le Verrier, the same guy who predicted the existence of Neptune with math alone, tried his hand at meteorology. And if you can predict a planet you've never seen, surely you can predict a cloud, right? Wrong. The atmosphere refused to cooperate. Here's where it gets really funny. The more instruments scientists built, the worse the problem seemed. It was like the atmosphere was mocking them. You'd think, if we measure more precisely, we'll get closer to the truth. But the opposite happened. Small differences in measurement would completely throw off the forecast. Predicting weather turned into a cosmic practical joke. Now, from a modern perspective, we can laugh. We know that the weather is chaotic. We know about Lorenz and his butterfly. But for people back then, it was maddening. They believed in the illusion of perfect prediction. They really thought that if you gave them enough thermometers and enough chalkboards, they could tame the sky. And the thing is, they weren't entirely wrong. Math did help. Weather forecasts today are pretty decent, at least in the short term, but the dream of total prediction, of being able to say exactly what the weather will be like weeks in advance, is still impossible, and it all comes back to chaos. But let's not get ahead of ourselves. At this stage of the story, in the 19th century, scientists were still living in that Newtonian bubble. They thought the world was neat and tidy, and that unpredictability was just a temporary problem. Once we have better equations, better instruments, and maybe a really, really big chalkboard, they thought, we'll predict everything. The irony is delicious, because in trying to predict the weather, they stumbled into the very system that would later prove their entire philosophy wrong. The atmosphere wasn't a giant clock. It wasn't a tidy equation. It was more like a jazz musician, improvised, unpredictable, beautiful, and sometimes just making noise to mess with you. So picture it. The 1800s are rolling along, scientists are drawing their charts, admirals are issuing their forecasts, farmers are still grumbling because it rained on their wheat anyway, and somewhere in the background, chaos is sitting there patiently, waiting to make its grand entrance. Soon, a butterfly will flap its wings, and the whole illusion of perfect prediction will come crashing down. Picture this. It's the early 1960s. The world is buzzing with optimism. We've got astronauts strapping themselves into rockets that are basically glorified tin cans with explosives underneath. Computers are starting to show up, but they don't look like your sleek little laptop. They look like refrigerators that went to the gym and bulked up way too much. And in the middle of all this, there's a quiet man named Edward Lorenz. He wasn't a flashy guy. He didn't have wild hair like Einstein, or a reputation for jewels like Newton and Leibniz. Lorenz was soft-spoken, modest, almost shy, but hidden behind that gentle demeanor was a brain that was about to ruin the illusion of order that math had been clinging to for centuries. Lorenz worked at MIT as a meteorologist, which basically meant he spent his life staring at numbers about the weather. And you might think, what a boring job, but no. This man had access to one of the early computers, and back then that was like being handed the keys to a spaceship. Computers in the 1960s couldn't play video games, couldn't browse YouTube, couldn't even run Minesweeper, but what they could do was crunch numbers at speeds no human could ever match. Lorenz was obsessed with predicting weather. Remember, meteorology had been the great unsolved problem for centuries, and here was Lorenz, thinking maybe, just maybe, these giant humming machines could finally solve it. So he set up a simple model of the atmosphere. Nothing too crazy, just a few equations to simulate convection, the way hot air rises and cool air sinks. The idea was to use the computer to run these equations over and over, simulating the atmosphere's behavior over time. One day Lorenz wanted to repeat a simulation he had already run, but he was in a hurry, and instead of typing in all the numbers again, he decided to take a shortcut. The computer printed out results with 3 decimal places, like 0.506, but inside the machine, it was actually storing 6 decimal places, like 0.506127. Lorenz thought, close enough, and typed in the rounded version. And that's when the universe decided to play a prank on him. When he ran the model with the rounded numbers, he expected to see the same weather pattern he had gotten before, maybe a little shift here or there, but basically the same. Instead, the results went completely off the rails. The pattern diverged dramatically, as if the computer had just decided, "Nah, I'm bored of your forecast. Let's invent a hurricane instead." Lorenz checked everything. Had he typed the numbers wrong? Was the machine broken? Did someone spill coffee on the circuits? But no, the only difference was that tiny rounding error, less than 1,000th. And yet, that tiny change had produced a totally different outcome. It was mind-blowing. Up until then, people thought small errors would produce small effects. If you're a little bit off, your prediction will be a little bit off, right? Wrong. Lorenz had just discovered that in certain systems, like the weather, a tiny difference in the starting point could explode into a completely different future. This was the birth of chaos theory. Now, here's the part that turned it from a nerdy math discovery into cultural legend. Lorenz tried to explain it to other people, and at some point he used a metaphor. Can the flap of a butterfly's wings in Brazil set off a tornado in Texas? It was the perfect image, a tiny, delicate thing causing massive consequences on the other side of the world. Of course, Lorenz didn't literally mean butterflies are out there plotting tornadoes. The point was that small causes can have huge, unpredictable effects in certain systems, but the image stuck. People loved it. The butterfly effect became one of the most famous metaphors in science. And the irony is, Lorenz didn't set out to revolutionize math. He was just trying to predict the weather. He thought he was solving a practical problem, not breaking the universe's idea of order. But that's how science works sometimes. You go looking for one thing, and you trip over something much bigger. Lorenz published his findings, but at first not many people paid attention. Chaos theory sounded a little too chaotic. Scientists prefer neatness. They like equations that give clean answers, not messy systems where a butterfly can wreck your forecast. For years, Lorenz's work was kind of ignored, sitting there like a time bomb. But gradually people began to realize how profound it was. The implications went way beyond weather. Suddenly mathematicians, physicists, economists, biologists, they all started wondering, wait, if the weather is sensitive to tiny changes, what about my system? What about my field? Could it all be butterflies? And the answer was yes. Butterflies everywhere. Here's where it gets funny. The phrase butterfly effect entered popular culture so fast that people started using it in ways Lorenz never intended. Movies, TV shows, and books made it sound like if you stepped on a butterfly in the past, you'd come back to the future and discover dinosaurs running your government, which, to be fair, would be more entertaining than most governments. But Lorenz's discovery wasn't really about time travel. It was about unpredictability in deterministic systems. That's a mouthful. So let's say it this way. The rules of the system are fixed, but the outcomes are sensitive to tiny, almost invisible changes. It's like baking a cake, where if you add one extra grain of sugar, instead of cake, you get lasagna. So let's pause and admire this moment. One man, one computer, one rounding error. That's all it took to crack open a door that had been locked since Newton's time. It's kind of poetic. Centuries of scientists marching around saying the universe is a perfect machine, and then along comes Lorenz pressing the wrong button on a clunky computer, and boom, chaos enters the chat. Think about how humbling that is. We humans love to feel like we're in control. We build our machines, we write our equations, we make our forecasts, and yet sometimes the tiniest thing, a butterfly's wing, a decimal place, reminds us that we're not the masters of the universe. We're just along for the ride. So there it is. The butterfly has entered the story. The world of neat predictions is starting to crumble. The weather, the proud fortress of order, has revealed itself as chaotic, and Lorenz, the quiet meteorologist, has become the accidental revolutionary. Next time you see a butterfly flutter by, give it some respect. That little insect may not literally control tornadoes, but thanks to Edward Lorenz, it represents something even bigger, the fragile line between order and chaos, and the reminder that even the smallest things can change everything. By the time Edward Lorenz stumbled on his little rounding error in the 1960s, he had no idea he'd just given birth to one of the most famous phrases in all of science. He wasn't sitting at MIT thinking, ah yes, Today I shall create a metaphor that will inspire movies, novels, and bad tattoos. Nope, he was just trying to rerun a weather simulation. But when the story of his discovery spread, people needed a way to describe it. You can't exactly walk up to someone and say, "Hey, did you know nonlinear differential equations in atmospheric convection are sensitive to initial conditions?" That's not going to get you invited to parties. So Lorenz came up with something better, the butterfly. Now, we don't actually know the exact moment he coined the image. What we do know is that in 1972, Lorenz gave a talk with the wonderfully dramatic title, Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? And that, ladies and gentlemen, is how legends are born. The talk was meant for scientists, but the metaphor escaped the lab almost immediately, because the butterfly effect isn't just catchy, it's sticky. It makes people picture this delicate, harmless creature causing chaos half a world away. It's poetic, it's absurd, and it perfectly captures the central idea: small changes can have enormous consequences. Of course, the reality is a little less glamorous. A single butterfly flapping in Brazil does not literally cause a tornado in Texas. If that were true, every butterfly would need its own criminal record. Imagine the headlines: "Monarch arrested for property damage in Oklahoma." No, what Lorenz meant was that the atmosphere is so sensitive that tiny differences in initial conditions, like the flap of a wing, can eventually lead to big differences in outcomes. It wasn't just scientists who loved this metaphor. Writers and artists jumped on it too. The butterfly effect began popping up everywhere. Science fiction writers used it to talk about time travel. The idea was, if you went back in time and accidentally stepped on a butterfly, you'd come back to the future and find everything changed. Dinosaurs in the White House, people eating spaghetti with their hands, who knows? One of the most famous early versions of this idea came from a short story by Ray Bradbury, published way back in 1952 before Lorenz's discovery. It was called A Sound of Thunder. In the story, time travelers go back to the age of dinosaurs. One of them panics, steps on a butterfly, and when they return home, the entire world is different. Language has shifted, politics have changed, everything is off. Bradbury didn't know about Lorenz's equations, but he tapped into the same deep truth. Little things can snowball into massive consequences. By the 1980s and 1990s, chaos theory had gone mainstream. You'd see it in pop culture everywhere. Jurassic Park, for example. Remember Jeff Goldblum's character, Dr. Ian Malcolm? He's the sarcastic, leather jacket-wearing chaos theorist who warns everyone that creating dinosaurs is a terrible idea. He literally explains the butterfly effect while dripping water on someone's hand. That scene turned Lorenz's discovery into Hollywood entertainment. And here's the funny thing. Most people who throw around the phrase butterfly effect don't really know where it came from. They just use it to sound mysterious. Like when your friend cancels dinner and someone says, "Well, you know, butterfly effect," as if skipping tacos tonight is going to cause a volcanic eruption next week. But behind the cliches, there's something profound. The butterfly effect is a reminder that the world is both deterministic and unpredictable at the same time. The rules don't change. Newton's laws still apply, the equations still govern motion, but tiny changes in the starting point can explode into giant differences later on. Deterministic chaos, that's the real punchline. And people found this both terrifying and comforting. Terrifying, because it meant total prediction was impossible. Even if you had the biggest supercomputer on Earth, you could never predict the weather months in advance with perfect accuracy. You could never know exactly how the stock market would move. You could never be completely certain what tomorrow would bring. But also comforting, because it meant the future wasn't carved in stone. It wasn't pre-written by Laplace's demon. There was wiggle room, uncertainty, a little chaos in the gears of destiny, and that chaos meant life could surprise us. Sometimes in terrible ways, yes, but also in wonderful ways. Lorenz himself wasn't a dramatic man. He didn't make bold philosophical speeches about free will or destiny. He was just a mathematician who noticed something strange in his numbers. But his discovery opened the door for other people to dream bigger. Philosophers, artists, and even spiritual thinkers started using chaos theory as a lens for their own ideas. The irony? Lorenz's original paper that started all this was published in 1963 in a journal called Tellus. The title wasn't flashy, it wasn't poetic, it was deterministic non-periodic flow. That's right, the butterfly effect started with possibly the least exciting title in academic history. If you're ever worried about your boring school essay title, just remember the paper that launched chaos theory could put you to sleep in the library. But the story didn't stay boring for long. Once people started visualizing Lorenz's equations, something magical happened. The solutions traced out patterns in three-dimensional space that looked like a butterfly, not a literal butterfly with wings and antennae, but a beautiful looping infinite curve, what's now called the Lorenz attractor. Suddenly, the butterfly metaphor wasn't just a metaphor, it was right there in the math, fluttering forever in the equations. So in a way, the butterfly effect named itself. The math drew wings, and Lorenz gave them a story. From then on, the butterfly became the mascot of chaos theory. Scientists studying nonlinear dynamics would decorate their books and papers with butterfly-shaped diagrams. Teachers would use it to hook students into learning, and the public loved it because it made math feel poetic, even magical. Think about it. How often does math get a metaphor that captures the imagination of the whole world? Usually math gives us things like non-periodic flow or partial differential equation of second order. Nobody's putting that on a movie poster. But butterfly effect? That sells tickets. That makes people lean forward and say, "Tell me more." And here's the best part. Lorenz never chased fame. He didn't try to brand himself as the butterfly guy. He just kept doing his research, kept living his quiet life. But his butterfly kept flapping, carrying his name into classrooms, movies, and conversations he probably never imagined. So the butterfly effect was born, not as a slogan, not as a meme, but as a discovery about how fragile and unpredictable the world really is. From a rounding error on a clunky computer to one of the most famous ideas in modern science. All because one man noticed that his numbers didn't line up, and instead of ignoring it, he paid attention. That's the magic of it. Chaos didn't start with a thunderclap or a revolution. It started with a whisper. The whisper of a butterfly's wings. Math has a reputation. Ask most people, and they'll tell you math is about rules, about order, about things behaving the way they're supposed to. 2 plus 2 is 4. The angles in a triangle add up to 180 degrees. Pi is irrational, but somehow always there when circles show up. Math is clean, sharp, and obedient. At least that's the myth. But every once in a while, math acts like a teenager. It rolls its eyes, slams the door, and refuses to follow the script. And nowhere is that more obvious than in chaos. Let's rewind a little. For centuries, mathematicians loved tidy systems. Things like planetary orbits. You could draw a neat ellipse, label it with Newton's equations, and boom, job done. The math behaved. It was like a polite student raising its hand in class before speaking. Then you toss in a system like weather, and suddenly math turns into that one kid who eats glue and throws pencils at the ceiling fan. Weather equations look fine at first. Fluid dynamics, heat transfer, all that good stuff. But when you try to actually solve them, they go completely off script. Tiny differences in input spiral into massive changes. Suddenly, instead of neat predictions, you've got spaghetti lines racing across your graph. This is what chaos really means in mathematics. Sensitive dependence on initial conditions. That's the official phrase. But let's not use official phrases. Let's put it this way. Chaos means math refuses to behave like you expect. It means small causes don't always lead to small effects. Instead, a decimal point out of place can snowball into disaster. And here's the kicker. It's not randomness. That's the trap people fall into. Chaos isn't the same thing as random noise. Randomness is like rolling dice. You literally have no idea what's coming, no matter what. Chaos is trickier. It's still deterministic. The rules are still there, the equations are still exact, but the outcomes are so sensitive that in practice it feels random. It's like the universe is technically playing by the rules, but in such a sneaky way that you can never keep up. Think of it like trying to herd cats. In theory, cats follow rules. They get hungry, they sleep, they chase shiny things. But in practice, good luck predicting what 12 cats will do in a room together. Will they nap? Will they fight? Will one of them crawl into your fridge? Yes, they're obeying their cat laws, but good luck writing equations for that. That's chaos. Mathematicians started to realize this wasn't just about weather. Chaos was everywhere. Double pendulums, for example. Take a pendulum, the kind you had on your grandma's clock, and add another pendulum dangling from it. Sounds innocent, right? But try to predict its motion. The thing starts swinging in ways that look completely wild. A tiny push at the beginning makes it swing in totally different patterns. It's like pendulum jazz. Or billiard balls. You'd think pool is just geometry, right? Angles, momentum, Newton's laws. But if you've ever actually played pool, you know better. The tiniest difference in how you hit the ball changes the whole game. The table turns into a chaos factory, which, by the way, is my excuse for being terrible at pool. It's not me, it's chaos theory. And here's a classic, dominoes. If you line up a neat little row of dominoes and push one over, everything looks predictable. They fall in order, but add in even a small irregularity, a wobble in the table, a slight gap between two pieces, and suddenly the whole pattern collapses in unexpected ways. The chain reaction doesn't care about your plans. That's chaos in miniature. For a long time, mathematicians didn't want to admit this stuff. It was embarrassing. You're supposed to be the high priests of order and certainty, and suddenly your equations are throwing tantrums. It's like being a chef and admitting you sometimes burn toast. Not a good look. But eventually the truth couldn't be ignored. Systems that should have been predictable weren't, and the reason wasn't bad data or human error. The reason was the math itself. The equations allowed for solutions that were wildly sensitive to initial conditions, which meant prediction had a built-in limit. You could only see so far into the future before everything dissolved into chaos. This realization was both frustrating and liberating. Frustrating because it crushed the dream of Laplace's demon, that smug little imaginary being that thought it could predict the entire universe. Sorry, demon. Turns out even you can't forecast the stock market or next Tuesday's thunderstorm. But it was also liberating, because it meant unpredictability wasn't a failure of science. It was a feature of nature. Chaos wasn't the enemy of math. Chaos was math showing us a new layer of reality. And honestly, chaos makes the world more interesting. Imagine if everything really were perfectly predictable. If you knew exactly what would happen every moment of your life, down to the second. Sounds safe, but also boring. Like watching paint dry on an infinite loop. Chaos is what gives us surprises, creativity, spontaneity. It's why jazz exists. It's why evolution works. It's why your uncle's barbecue sometimes ends with fireworks, even though nobody planned it that way. So when math refuses to behave, it's not being rude. It's just showing you the universe's personality. A little bit of order, a little bit of disorder, mixed together in just the right amount to keep things spicy. Lorenz's butterfly was the poster child for this revelation. But the deeper message went far beyond butterflies. It was this: even in a world governed by strict rules, unpredictability is baked into the cake. Chaos is part of the recipe. And once you see it, you start spotting butterflies everywhere. In the weather, in the stock market, in your kitchen experiments, in your daily commute. So next time your math doesn't behave, don't panic. Don't throw your calculator out the window. Just smile and remember, sometimes misbehaving math is the most honest math of all. Because chaos isn't a mistake, it's the universe winking at us, reminding us that certainty is an illusion. And honestly, that wink makes the whole ride a lot more fun. If you've ever played a game with dice, you know the feeling. You shake them up, you toss them across the table, they bounce around like tiny cubes of destiny, and then bam, double sixes, or maybe snake eyes. And in that moment, your entire evening changes. Suddenly you either win a pile of fake Monopoly money, or you flip the board and storm out of the room. Dice are such simple objects, just cubes with numbers on them, but they represent something bigger. To most of us, dice mean randomness, chance, the role of fate. But to mathematicians, dice are also a reminder of something deeper, how hard it is to tell the difference between randomness and chaos. Let's start with the obvious. If you roll one die, the outcome is basically unpredictable. You might think you can control it, throw it harder, flick your wrist just right, but unless you're secretly a dice magician, you're not predicting that six. It feels random. But here's the weird part. In theory, dice aren't random at all. They're physical objects obeying the laws of physics. Newton's equations still apply. If you could measure the exact angle of your hand, the exact force, the exact bounce off the table, you could calculate the outcome every single time. The only reason dice feel random is because it's impossible to know all those details perfectly. A tiny change in how you throw them makes a huge difference in the result. Sound familiar? That's chaos theory in action. Now let's move to another childhood favourite, dominoes. Setting up dominoes is one of those activities that feels innocent but is secretly training you to understand chaos. You line them up, carefully, one after the other. Maybe you even get ambitious and build curves, spirals, or the famous domino rally that your cat will absolutely destroy before you finish. The fun comes when you tap the first domino. Everything topples in a perfect chain reaction. At least that's the dream. In reality, there are always surprises. One domino falls a little too far, misses the next one, and the whole chain grinds to a stop. Or worse, a random vibration knocks over the chain before you're ready, and your masterpiece collapses while you're still halfway through. Chaos again. The domino effect seems predictable. Push one, they all fall, but it's incredibly sensitive to small imperfections. The tiniest misalignment, the tiniest wobble, and the outcome changes. And once things go wrong, there's no recovering. You can't pause the chain halfway and reset it. The system evolves too fast for you to interfere. That's the essence of chaos. Once it starts, you're just along for the ride. And then there's billiards, or pool, depending on how you like to name it. On paper, pool is the most mathematical game ever. Angles, momentum, collisions. It's a physicist's dream. You could, in theory, write down equations for the path of every ball. But if you've ever actually played, you know it doesn't work like that. The tiniest difference in how you strike the cue ball leads to totally different outcomes. The balls scatter, ricochet, and suddenly that one shot that was supposed to look smooth and professional turns into complete chaos. That's the dirty secret of deterministic systems. They follow rules, but the rules don't guarantee predictability. In a chaotic system, small changes blow up into big effects. It's the difference between neat textbook physics and messy reality. And here's where things get fun. Mathematicians and scientists realized that chaos wasn't just hiding in weather or fancy equations, it was everywhere. Dice, dominoes, billiard tables, pendulums, even double pendulums, the ultimate overachievers of chaos. Everyday objects that looked simple turned out to be gateways into unpredictability. Here's a story for you. In the 1980s, researchers actually built machines to roll dice under controlled conditions. They thought, if we roll them the same way every time, we'll crack the code, and for a little while they could predict outcomes with decent accuracy. But eventually, tiny imperfections in the surface, air resistance, even temperature differences messed everything up. The predictions broke down, chaos won. Dominoes tell a similar story. Engineers have studied chain reactions to understand how small failures can trigger massive collapses. It's not just toys, it's power grids, financial markets, even ecosystems. A single failure can cascade through a whole system. The metaphor of falling dominoes became so famous that presidents use it in speeches. Remember the domino theory in politics? The idea that if one country fell to communism, the neighbouring countries would topple too? Yep, politicians basically stole the language of chaos to explain geopolitics. But here's the funny thing about chaos. It doesn't always lead to destruction. Sometimes it creates beauty. Domino artists build massive structures that collapse in breathtaking patterns. Pool trickshot artists use chaos to their advantage, making the balls dance across the table in ways that look impossible. Even dice, symbols of randomness, have inspired art and probability theory. Chaos is messy, but it's also creative. That's the paradox. Out of unpredictable behavior, you sometimes get patterns, fractals, strange attractors, repeating shapes. It's like the universe is saying, yeah, I'm going to be unpredictable, but I'll do it with style. Think about it this way. If dice always rolled in perfect sequence, if dominoes always behaved flawlessly, if billiard balls always followed simple lines, life would be boring. There'd be no drama, no surprises, no wow moments. Chaos makes the world feel alive. Of course, it also makes life frustrating. Just ask anyone who's ever lost money gambling on dice or betting on pool. Humans love to think we can beat chaos. We build casinos on that belief. And casinos in return build enormous hotels on our losses. But in the bigger picture, these little games with dice and dominoes are just miniature lessons in humility. They remind us that control is an illusion, that the tiniest nudge, the smallest flap of wings, can change everything. And maybe that's why people find chaos so fascinating. It's not just math, it's a philosophy. It's a reminder that life is not a neat equation, but a chain reaction, a scatter of dice, a tumble of dominoes, unpredictable, frustrating, sometimes hilarious, but always surprising. So next time you throw dice, or line up dominoes, or take a shot at the pool table, remember, you're not just playing a game, you're staring chaos right in the face, and chaos is smiling back, daring you to predict what comes next. If chaos theory were a movie, the butterfly effect would be the flashy trailer, the part everyone remembers. But the real star of the show, the thing that mathematicians stare at with awe, is something called a strange attractor. I know, it sounds like the name of a band that only plays in basements and insists on selling their CDs out of a cardboard box. But strange attractors are not indie musicians. They're patterns, beautiful, infinite patterns that live inside chaos. Let's rewind to Edward Lorenz again. Remember how he was running those weather equations on his clunky 1960s computer? When he plotted the solutions in 3 dimensions, he expected to get something boring. Maybe a line, maybe a circle, maybe just numbers wandering around like a lost tourist. Instead, the solutions started looping and swirling, but they didn't repeat. And yet this is the mind-blowing part. They didn't wander off randomly either. The system kept tracing out the same overall shape, over and over, like it was trapped inside an invisible boundary. That shape looked like 2 butterfly wings glued together. This was the Lorenz attractor. Now, why call it an attractor? Because in dynamical systems, an attractor is where things tend to end up. Imagine dropping a marble into a bowl. No matter where you drop it, it rolls around and eventually settles at the bottom. That's a simple attractor. Predictable, boring, like a cat falling asleep in the same sunny spot every day. But a strange attractor? That's different. Instead of settling down, the system keeps moving forever, never repeating exactly, but never escaping either. It's like a chaotic dance that somehow stays inside the same ballroom. You get endless variety, but also a hidden order. That's the strange part. Lorenz's butterfly-shaped attractor was one of the first ever discovered, and it became iconic. Scientists printed posters of it. Mathematicians framed it on their walls. College kids got it tattooed on their arms because nothing says I'm deep like a set of nonlinear differential equations carved into your skin. What makes strange attractors so fascinating is their mixture of order and chaos. Up close, the path looks unpredictable, messy, wild. But step back and you see the larger shape. It's chaos contained, disorder wrapped in order. The universe's way of saying I might be unpredictable, but I've got style. Here's an analogy. Imagine you're listening to jazz improv. At first, it sounds like the saxophone player is just making random noises. But after a while, you realize there's a structure. There's a key, a rhythm, a groove that holds everything together. Strange attractors are like the jazz of mathematics. Improvised, wild, but still following an invisible score. And they're everywhere. Scientists have found attractors in weather systems, in fluid turbulence, in chemical reactions, even in the beating of the human heart. If your heartbeat were perfectly regular like a metronome, that would actually be unhealthy. Real hearts have tiny variations, little chaotic shifts, but they're not random. They live inside an attractor, a healthy kind of chaos. Step outside that attractor, and suddenly you're in arrhythmia. Not good. One of the most famous strange attractors, discovered by Mitchell Feigenbaum, lives in something as innocent as a dripping faucet. Yes, the thing in your kitchen sink. Turn on the tap just enough, and the drops start falling. At first, they're regular, plop, plop, plop. Then, as you tweak the flow, the pattern starts to wobble. Plop, plop, pause, plop. Keep tweaking, and suddenly the dripping turns chaotic. But if you measure it carefully, the times between drops aren't random. They follow a strange attractor. Your sink is secretly doing chaos math while you brush your teeth. Even more fun, computer graphics artists love strange attractors because they look gorgeous. Fractals, spirals, endless swirling shapes that never quite repeat. They've shown up on album covers, in screensavers if you're old enough to remember those, and in psychedelic posters. Who knew meteorology could produce something that belongs on a Pink Floyd t-shirt? But here's the kicker. Strange attractors tell us something profound about the universe. They say, chaos is not just noise. It has hidden structure. Systems that look wild and unpredictable still live inside invisible boundaries. You can't predict the exact future, but you can know the shape of possibilities. Think about that. Life is kind of like a strange attractor. You can't predict exactly what will happen tomorrow. Will you spill coffee on yourself? Will you meet a stranger who changes your life? No idea. But your life doesn't just fly off into infinite randomness either. It loops within a certain shape. Your habits, your choices, your circumstances. A strange attractor of existence. Lorenz himself once said that the most important idea wasn't that weather was unpredictable, but that unpredictable systems could still have underlying order. That was the revolutionary shift. Before chaos theory, scientists thought systems were either predictable or random. After Lorenz, we learned there's a third category, chaotic but structured. And here's a fun fact. Mathematicians studying strange attractors often talk about basins of attraction. Imagine pouring water on a landscape. Depending on where you pour, it flows into one valley or another. Those valleys are basins of attraction. Your system might wander chaotically, but it's still stuck in its basin, kind of like your dog. He might run around the yard in wild loops, but he's still inside the fence. Of course, explaining this to the general public was tricky. Non-linear dynamical systems with fractal attractors doesn't exactly roll off the tongue. That's why the butterfly image was so perfect. It gave chaos theory a logo, a brand. And in science, just like in business, branding matters. The butterfly made chaos theory famous, but the strange attractors gave it substance. So next time you see one of those swirly, hypnotic images of a Lorenz attractor, don't just think cool pattern. Think that's math showing me the boundary between order and disorder. That's the geometry of chaos. And if you want to sound extra smart at a party, you can lean over and say, "Did you know your heartbeat is basically a strange attractor?" Just make sure to follow it up with a joke, or people might slowly edge away from you. If there's one thing humans have always wanted to control, it's the weather. Forget flying cars and robot butlers. If you gave people the choice between those, or never having to deal with rain on their wedding day, I'm pretty sure weather control would win every time. For thousands of years, the weather was treated like a divine prank. Ancient civilizations made sacrifices, danced rituals, and prayed to weather gods. The Greeks had Zeus with his lightning bolts. The Vikings had Thor with his hammer. Farmers everywhere built temples and begged the sky for a good harvest. Because honestly, what else could they do? If it rained, it rained. If it didn't, you starved. End of story. By the 19th century, though, science was on a roll. Newton had given us a clockwork universe. Laplace had bragged about his demon that could predict everything. Steam engines were puffing across continents. Telegraphs were zapping signals faster than horses could run. And people thought, hey, maybe we can finally beat the weather at its own game. Meteorology was born. And it was serious business. Governments poured money into building networks of weather stations. They trained observers to measure temperature, pressure, wind, humidity, every detail they could think of. The telegraph allowed these observations to be transmitted in real time, creating the first big data sets in history. Suddenly, people weren't just staring at clouds and guessing. They had numbers, glorious numbers. But as anyone who's ever been lied to by a weather app knows, numbers aren't always enough. Predictions kept failing. Armies marched into storms. Farmers lost crops. Entire shipping fleets sank in tempests nobody saw coming. The dream of total weather prediction slipped further away every time reality reminded them. Nature doesn't like to be bossed around. Let's talk about some characters. One of my favourites is Robert Fitzroy, the same guy we met earlier, captain of the HMS Beagle, babysitter of Charles Darwin, inventor of the word forecast. He was a pioneer building storm warning systems and trying to give people a fighting chance against the skies, but his forecasts often missed the mark, and the press mocked him ruthlessly. They literally called his work Fitzroy's guesses. Imagine dedicating your life to protecting sailors and farmers, and the newspapers dunk on you harder than a basketball player at the Olympics. It crushed him. His story is tragic, but he laid the foundation for the modern weather service. Then there were the French. Urbain Le Verrier, famous for predicting Neptune's existence using pure math, thought he could conquer meteorology too. Neptune, sure. Clouds? Not so much. Turns out it's easier to predict a planet millions of kilometers away than a rainstorm happening next week. But the biggest blow came from chaos itself. Scientists kept assuming that if they just measured better, if they built more precise instruments, the forecasts would improve. And to some extent they did. Short-term forecasts got pretty good. You could predict tomorrow's weather with reasonable accuracy, But long-term, forget it. Every time they pushed further into the future, the predictions unraveled. And here's why. The atmosphere is chaotic. Tiny differences like whether one butterfly flaps its wings make a huge difference days later. Even with perfect equations, even with the most powerful supercomputer, there's a hard limit on predictability. You can only see a certain number of days ahead before the system becomes unknowable. Meteorologists call this the predictability horizon. Beyond about 10 to 14 days, the forecast is basically useless. You might as well flip a coin. And that's not because meteorologists are bad at their jobs. It's because chaos theory says so. It's literally baked into the math. This drove 20th century scientists nuts. On the one hand, they could launch rockets to the moon, split atoms, invent lasers. On the other hand, they still couldn't tell if it was going to rain on your picnic next Saturday. Talk about humbling. But instead of giving up, meteorologists got clever. They invented something called ensemble forecasting. Instead of running one simulation of the atmosphere, they run dozens or even hundreds, each with slightly different starting conditions. Then they compare the results. If most of the simulations say rain, you pack your umbrella. If half say rain and half say sunshine, you cancel the picnic and stay inside with Netflix. It's not perfect, but it works. And it's basically an acknowledgement of chaos. Meteorologists can't predict one exact future, but they can give you probabilities, a cone of possible outcomes. It's the best compromise between order and disorder. And speaking of compromise, let's not forget the Cold War. Weather prediction wasn't just about farmers anymore, it was about national security. If you could predict storms, you could plan military operations. If you could model the atmosphere, maybe you could even control it. Yes, governments seriously tried. Project Storm Fury, for example, was an American attempt to weaken hurricanes by seeding clouds with silver iodide. Spoiler, it didn't work. The hurricanes basically laughed and kept spinning. The Soviets, never ones to be outdone, had their own weather control fantasies. There were proposals to melt the Arctic ice cap with nuclear bombs, redirect rivers, and basically remodel the planet like it was a Minecraft server. None of that happened, thankfully, but it shows just how desperate humans were to win the war against weather. Today, we've accepted defeat. We don't control the weather, and we never will, but we've made peace with it. Forecasts are good enough to warn us about hurricanes and give us a few days' notice for snowstorms. And honestly, that's a victory. Because in a chaotic system, good enough is the best you're ever going to get. The war against weather wasn't really a loss. It was a lesson. It taught us that not everything can be tamed. Some systems are inherently unpredictable. Some mysteries stay mysterious. And that's okay. If we could predict everything, life would be boring. So the next time your weather app lies to you, don't blame the meteorologists. Don't even blame the app. Blame chaos. Blame the butterfly. Blame the universe's refusal to behave like a neat equation. Because the truth is, the war against weather was never about defeating nature. It was about learning humility. And in that sense, chaos won. But maybe that's not such a bad thing. So far, we've seen chaos in weather, in dice, in dominoes, in the stubborn refusal of math to sit quietly and behave. But chaos doesn't just live in labs or computer simulations. It's out there in the wild, in forests, in oceans, in traffic jams, even inside our own bodies. Nature is basically chaos theory's playground. Let's start with animals. Imagine you're watching a population of rabbits in a meadow. At first it looks simple. Rabbits eat, rabbits make more rabbits, rabbits bounce around being adorable. Then you add foxes. Foxes eat rabbits, fewer rabbits survive, foxes multiply, and then boom, things swing the other way. Too many foxes, not enough rabbits, foxes starve, rabbit population bounces back. You'd think you could just write down some neat equations and predict the cycles forever. This is where the famous Lotka-Volterra equations come in. These are equations designed to describe predator-prey dynamics. On paper, it looks beautiful, wavy little cycles of rabbits and foxes dancing forever in predictable harmony. In reality, not so much. Throw in tiny variations, one rabbit gets sick, one fox gets lazy, and suddenly the entire system goes wild. Populations crash, rebound, explode, collapse. Ecologists quickly learn that ecosystems aren't neat oscillators, they're chaotic. And it's not just rabbits and foxes. Insects, birds, fish, even bacteria all show chaotic population dynamics. A tiny shift in climate, a tiny mutation, or even a butterfly flapping its wings, and suddenly entire food chains behave in unpredictable ways. That's why conservation biology is so hard. You can't just protect one species and expect everything else to behave. Nature doesn't work that way. Speaking of unpredictability, let's talk about locusts. These little grasshoppers are mild-mannered most of the time, but every so often they flip into swarm mode and cover entire regions in a moving cloud of chaos. Farmers panic, governments scramble, and billions of crops vanish. Scientists still struggle to predict when and why the swarms happen. Tiny changes in population density, rainfall, or temperature can flip the switch. Chaos theory hiding inside a bug's brain. Now, let's zoom out. Whole ecosystems follow the same rules. Rainforests, coral reefs, savannas, they all operate on delicate balances that look stable until suddenly they're not. One drought, one invasive species, one human bulldozing a little too much land, and the system tips. Chaos cascades. It's like toppling dominoes, except the dominoes are trees, rivers, and entire species. And it's not just biology. Chaos shows up in geology too. Think about earthquakes. Tectonic plates are grinding against each other all the time. You'd think we could predict when and where they'll slip. Scientists have tried. They measure stress, collect data, run simulations, but earthquakes refuse to schedule themselves neatly. A tiny crack can grow into a catastrophic rupture, or nothing might happen for decades. The system is deterministic. Rocks follow physics, but so sensitive that prediction is basically impossible. Sound familiar? Yep, chaos again. Now let's bring it closer to home. Literally, traffic. You'd think driving down the highway would be straightforward. Cars move, keep distance, obey rules. But if you've ever been stuck in a traffic jam with no visible cause, congratulations, you've witnessed chaos in action. Researchers have shown that traffic jams can appear spontaneously, with no accident, no construction, no reason at all. One driver taps the brakes a little too hard, the ripple spreads backward, and suddenly miles of cars are at a standstill. It's like a domino effect with SUVs. Japanese scientists even staged this. They put cars on a circular track and asked drivers to maintain steady speed. At first, everything looked fine, but within minutes, little ripples appeared, waves of braking and accelerating, until a full-on phantom traffic jam emerged. Nobody caused it, but everybody experienced it. That's chaos theory taking the wheel. And if you think humans are unpredictable, wait until you look at the weather of animal migrations. Birds, fish, even crabs move in massive groups across the planet. At first glance, it looks like a perfect system. Birds fly in V formations, fish school in shimmering waves, but the patterns are astonishingly sensitive. A gust of wind, a single predator, or a minor climate shift can send entire migrations off course. Chaos doesn't just lurk, it flaps, swims, and scuttles in plain sight. Even your own body isn't safe. Your heart, for example. A healthy heartbeat isn't perfectly regular. It has slight variations that keep it adaptable, but push it too far into disorder, and you get arrhythmia, chaos in the rhythm of life. Your brain, too. Neurons fire in complex, chaotic patterns. That's part of what makes thought and creativity possible. But shift too far and it becomes epilepsy. Chaos again. Balancing between beauty and breakdown. And here's the kicker. Scientists didn't just find chaos in biology and geology by accident. They started looking for it, because Lorenz and his butterfly proved it could hide in everyday systems. Once you know the world is sensitive to tiny nudges, you start noticing butterflies everywhere. In ecosystems, in earthquakes, in traffic, in your bloodstream. But don't get depressed. Chaos isn't just destruction, it's also resilience. A chaotic system can absorb shocks, adapt, and keep going. Forests regrow after fires. Animal populations rebound after crashes. Even traffic clears eventually. Chaos makes life unpredictable, but it also makes it flexible. If everything were perfectly ordered, one small disruption could break the whole thing. Chaos gives the world wiggle room. Think about it this way. If nature were perfectly predictable, Earth might have stayed stuck with boring single-celled organisms forever. But chaos, mutation, accidents, random seeming swings drove evolution. Without chaos, no rabbits, no foxes, no humans to sit here talking about rabbits and foxes. So the next time you see a flock of birds suddenly change direction in perfect unison, or you get stuck in a traffic jam that seems to come from nowhere. Remember, you're looking at chaos in the wild. It's everywhere, shaping the world in ways we'll never fully control. And maybe that's a good thing, because if nature followed neat little equations forever, life would be static, predictable, boring. Instead, chaos keeps the story moving. Every good story needs characters. Heroes, villains, a few eccentrics. And chaos theory has some of the most colourful personalities in the history of math. These weren't the kind of people who just sat quietly with a notebook. No, these were the mad geniuses who peered into the abyss of unpredictability and said, "Yeah, I like it here." Let's start with Henri Poincaré, the French mathematician from the late 1800s. If Newton was the rock star of classical mechanics, Poincaré was the jazz musician who went off script. He was studying the infamous three-body problem, how three objects move under each other's gravity. Sounds simple, right? Sun, Earth, Moon. Easy. But the math turned into spaghetti almost instantly. Poincaré discovered that small changes in the initial conditions could completely alter the system's behavior. That's chaos right there, decades before Lorenz. In fact, he's sometimes called the true grandfather of chaos theory. The funny thing? He didn't have computers to draw fancy butterfly shapes. He just had pen, paper, and a brain that refused to quit. And he still managed to glimpse the shadow of chaos long before the rest of the world caught on. Then came Edward Lorenz, our soft-spoken meteorologist. We've already met him, with his clunky computer and his rounding error that shook science. Lorenz wasn't flashy either. He didn't go around calling himself a revolutionary, but his butterfly metaphor turned him into an accidental celebrity. Imagine being a shy math professor, and suddenly people are quoting you in Hollywood movies. Lorenz must have been quietly baffled by how far his little decimal mistake flew. But if Lorenz was the reluctant father of chaos, Mitchell Feigenbaum was its rebellious teenager. Feigenbaum worked at Los Alamos National Laboratory in the 1970s. Yes, the same Los Alamos where they built the atomic bomb. But instead of working on weapons, Feigenbaum was tinkering with equations about dripping faucets and logistic maps. Very glamorous. He discovered something wild. Chaos had universal patterns. For example, if you take a simple system like a population of rabbits growing over time, and you tweak how fast they reproduce, you see predictable cycles, 1 generation, 2 generations, 4 generations, and then suddenly, boom, chaos. But the way it happens isn't random. Feigenbaum found that the transition to chaos follows a precise ratio. The same ratio shows up in completely different systems. It was like finding a cosmic fingerprint hidden in disorder. Today, it's called the Feigenbaum constant. And yes, mathematicians geek out about it, the way teenagers geek out about Taylor Swift. Then we have Benoit Mandelbrot, the eccentric mathematician who gave the world fractals. If Lorenz gave chaos its butterfly, Mandelbrot gave it its wardrobe. He looked at coastlines, clouds, and cauliflower, and realized they all had the same jagged, self-similar geometry. He invented the term fractal to describe shapes that repeat themselves at different scales. Zoom in, zoom out, it's the same pattern forever. Mandelbrot was a character. He worked at IBM, wore eccentric suits, and loved to stir things up. He once said, "Clouds are not spheres, mountains are not cones, coastlines are not circles," which sounds obvious, but was actually a bold declaration against the clean, smooth shapes mathematicians preferred. Mandelbrot basically told the math world, "Your shapes are boring, nature is jagged and weird, deal with it." And then he drew the Mandelbrot set, one of the most famous images in mathematics, a fractal that looks like a psychedelic snowman. And let's not forget the philosophers of chaos, people like James York, the American mathematician who actually coined the term chaos in the scientific sense in the 1970s. Before that, scientists were too polite to call it that. They used phrases like nonlinear dynamics and sensitive dependence. York just cut through the jargon and said, "Let's call it what it is, chaos." And suddenly, everyone was paying attention. These mathematicians weren't just number crunchers. They were visionaries. They saw patterns where others saw noise. They embraced disorder when the rest of science wanted neatness. And they didn't mind being called a little mad. After all, chaos theory itself sounds like something a slightly unhinged scientist would invent in a comic book. But here's the thing. These mad mathematicians didn't create chaos. They revealed it. They showed us what was hiding in plain sight. The dripping faucet in your kitchen, the clouds in the sky, the heartbeat in your chest. They gave us the language to see it. And like all great characters, they didn't always get along. Mandelbrot, for example, loved to poke at traditional mathematicians who dismissed his work as just pretty pictures. Feigenbaum battled with skeptics who thought his universal constants were coincidence. Even Lorenz's butterfly got flack from scientists who thought the metaphor was too whimsical. Chaos theory wasn't welcomed with open arms. It had to fight its way into respectability, one eccentric mathematician at a time. Today, these figures are celebrated. Poincaré is remembered as a genius ahead of his time. Lorenz is the quiet hero. Feigenbaum is the constant guy. Mandelbrot is the fractal king. And York is the one who gave chaos its name. Together they built a revolution. And maybe they had to be a little mad to do it, because it takes a certain personality to stare at equations that refuse to behave, to keep pushing when everyone else says, "Forget it, it's too messy." These were people who saw beauty in disorder, who found meaning in unpredictability. In other words, the perfect cast for the wildest story math has ever told. If chaos theory had an art gallery, fractals would be the main exhibit. They're the posters, the screensavers, the psychedelic wallpapers of mathematics. Fractals are what happens when math decides to stop being shy and go full rock concert visuals. The word itself, fractal, was invented by Benoit Mandelbrot in the 1970s. Before that, mathematicians just called these shapes weird and pretended they didn't exist. Mandelbrot looked at nature and said, "Wait a second, clouds don't look like spheres, mountains don't look like cones, trees aren't perfect cylinders, and coastlines are definitely not straight lines." Which is true. If you've ever looked at a map and thought, why is the shoreline so squiggly? That's fractals at work. Let's start with the famous Mandelbrot set. If you've never seen it, imagine a little black snowman with a bunch of frilly edges, surrounded by psychedelic colors. Zoom in, and the edges keep revealing more detail. Zoom again, and you see new shapes, spirals, lightning bolts, seahorse tails, patterns repeating forever. No matter how far you zoom, there's always more. It's like the universe's version of Russian nesting dolls, except it never ends. And here's the kicker. The Mandelbrot set comes from an incredibly simple equation. It's literally just ZU Z² C. That's it. One line. But if you keep applying it over and over, the boundary of solutions draws this infinite complex masterpiece. It's like scribbling 2 + 2 and accidentally discovering the Mona Lisa. Fractals aren't just pretty pictures. They're the geometry of chaos. Strange attractors like Lorenz's butterfly are fractals. Population models that swing into chaos draw fractal patterns. Even random-looking systems, when plotted carefully, reveal fractal structures. It's like chaos has a signature, and that signature is fractal. But what makes fractals really magical is that they show up everywhere in nature. Look at a tree. The trunk splits into branches. The branches split into smaller branches. The smaller branches split into twigs. Each part looks like a tiny version of the whole. That's self-similarity, the hallmark of fractals. The same pattern repeats at different scales. Snowflakes? Fractals. Lightning bolts? Fractals. Blood vessels in your body? Fractals. Romanesco broccoli, that funky green vegetable that looks like it escaped from an alien planet, is a fractal you can eat. Nature loves this trick because it's efficient. Fractals pack a lot of complexity into simple rules. Take your lungs. They're basically fractals. Each bronchial tube splits into smaller and smaller branches until you've got millions of tiny air sacs. This branching structure gives you a gigantic surface area, all crammed neatly into your chest. If your lungs were smooth spheres, you'd barely get enough oxygen to climb a flight of stairs. Fractals keep you alive. Even coastlines are fractals. This blew mathematicians' minds when Mandelbrot pointed it out. The length of a coastline depends on how closely you measure it. If you measure with a ruler the size of a country, it looks short. If you measure with a ruler the size of a pebble, it's much longer. Zoom in forever, and the squiggles never smooth out. Coastlines have infinite complexity, which means technically, asking how long is Britain's coastline is like asking how long is infinity. The answer is, it depends. But fractals aren't just sitting there looking pretty. They also explain chaos in a practical way. For example, financial markets. Stock prices look random, but Mandelbrot noticed they had fractal patterns. The ups and downs repeat at different scales. Daily, weekly, yearly. Economists hated him for pointing this out, because it meant their neat equations for markets were wrong, but traders loved it, because it explained why markets swing wildly when nobody expects it. Chaos, fractals, Wall Street, all tangled together. And then there's art. Once fractals were discovered, artists jumped in immediately. Fractal landscapes in movies, computer-generated mountains, psychedelic posters. If you've ever stared at a screensaver that zooms endlessly into swirling colors, that's fractal math in action. It's like meditation, except you can do it with Windows 95. The beauty of fractals is that they bridge the gap between order and chaos. They're chaotic because they never exactly repeat, but they're ordered because the same structure appears at every scale. It's disorder with a rhythm, a jazz solo in geometry form. And here's something philosophical. Humans love symmetry. We build squares, circles, neat little triangles. But the universe prefers fractals. Jagged, messy, infinite, self-similar. Look around and you realize that nature isn't a straight line, it's a fractal. And once you see that, you can't unsee it. Mandelbrot himself was kind of a fractal. His career branched out everywhere. Math, physics, finance, art. He didn't fit neatly into one category, and his ideas kept repeating across disciplines. He once said, "Fractals are not just a curiosity, they are a new geometry of nature," and he was right. So the next time you look at clouds drifting overhead, or watch lightning zigzag across the sky, or cut open a piece of broccoli, take a moment. You're looking at chaos wearing its fractal costume. It's messy, it's infinite, it's strangely beautiful. And here's the secret. It's also a reminder, because if infinite complexity can come from a simple equation, maybe life's chaos isn't meaningless after all. Maybe there's hidden structure in the madness, waiting for us to notice. By the time Edward Lorenz gave his talk in 1972 about a butterfly in Brazil flapping its wings and possibly causing a tornado in Texas, he had no idea he was about to create one of the most famous metaphors in history. Scientists liked it, sure, but culture grabbed that butterfly, strapped a jetpack on it, and sent it flying into movies, novels, philosophy, and even sitcoms. Let's start with literature. Ray Bradbury had already beaten Lorenz to the punch with his short story, A Sound of Thunder, back in 1952. In it, time travelers go back to the age of dinosaurs. One of them panics, steps on a butterfly, and when they return to the future, bam, the world is completely changed. Language is different, politics have shifted, everything is off. Bradbury's butterfly was less about weather systems and more about time travel, but the message was the same: tiny actions can have massive consequences. Then came Hollywood. If there's one movie that made chaos theory cool, it was Jurassic Park in 1993. Enter Jeff Goldblum as Dr. Ian Malcolm, the world's most sarcastic chaos theorist. He sits there in his leather jacket, smirking while dinosaurs roar in the background, and explains to the audience that you can't predict complex systems. In one famous scene, he demonstrates the butterfly effect by dripping water on someone's hand. Depending on the tiniest variation, the droplet runs left or right. And the whole point, life finds a way. Chaos can't be contained. Dinosaurs will eat your lawyer, no matter how tall your electric fences are. The butterfly effect became such a buzzword that it even got its own movie creatively titled The Butterfly Effect, starring Ashton Kutcher. The movie took the metaphor literally. Change one small event in the past and the future unravels in wild, unpredictable ways. Critics weren't impressed, but the title stuck in everyone's brain. Suddenly, even people who had never heard of Lorenz or chaos theory were nodding wisely and saying, "Ah yes, the butterfly effect." But it wasn't just science fiction. The butterfly made its way into philosophy and everyday conversation. People started using it as shorthand for any small action with big consequences. Cancel your coffee date. Butterfly effect. Forget your umbrella. Butterfly effect. Spill soup on your shirt at lunch and end up meeting your soulmate because they handed you a napkin? Definitely butterfly effect. The metaphor escaped the lab and became a cultural meme long before memes were even a thing. TV shows picked it up too. The Simpsons had an episode where Homer travels back in time, steps on a butterfly, and returns to a future where Ned Flanders rules the world. Family Guy parodied it. Even children's cartoons started throwing in butterfly jokes. It became one of those ideas that everyone recognizes, even if they couldn't explain the math behind it if their life depended on it. And honestly, that's part of the beauty. Chaos theory could have remained locked in academic journals, buried under words like nonlinear dynamics and deterministic sensitivity. Instead, it got a symbol, a butterfly, a simple poetic image that everyone understands, and culture ran with it. Even music has had its butterfly moments. Songs and album titles reference it. Bands use fractals and chaos-inspired visuals in their cover art. If you've ever seen those swirling, infinite fractal images on a psychedelic poster, that's chaos theory sneaking into pop culture. It's math disguised as art. And speaking of art, fractals inspired entire movements in digital design. Once computers got powerful enough to render them, artists realized they could create infinite landscapes, impossible spirals, and hypnotic patterns with just a few lines of code. Suddenly, chaos theory wasn't just a metaphor, it was an aesthetic. Screensavers in the 90s, chaos theory. Those trippy animations that look like they belong at a rave, chaos theory again. But here's the funny twist. Pop culture tends to exaggerate. In movies, the butterfly effect often means one tiny action leads to wildly dramatic outcomes, like entire civilizations collapsing because you sneezed at the wrong moment. Real chaos is subtler. Yes, small changes can lead to big differences, but not every butterfly creates a tornado. Sometimes it just creates a breeze. Sometimes nothing happens at all. Still, the metaphor stuck because it resonates with how we experience life. We all have those moments where a small decision changes everything. Take the wrong bus and you meet someone who becomes your best friend. Miss a flight and you end up discovering a new city. Drop out of one class and accidentally fall in love with another subject. Humans are wired to find meaning in these chain reactions, and the butterfly effect gives us the language to talk about them. It also taps into something deeper, our fascination with fate versus chance. If small actions ripple out into the future, are we really in control of our lives, or are we just butterflies flapping our wings, sending invisible waves into the world? Chaos theory doesn't answer that question, but it sure makes it fun to ask. And of course, once the internet came along, the butterfly effect exploded again. Memes, Reddit threads, TikToks, all filled with butterfly jokes and what-if scenarios. It's one of those scientific metaphors that refuses to die because it's too good, too catchy, too relatable. Edward Lorenz never sought fame. He probably would have been happy just publishing his papers and tinkering with weather models. But his butterfly escaped into the wild, and once it landed in pop culture, it multiplied like butterflies. So the next time you hear someone casually drop the butterfly effect into conversation, remember where it came from. It wasn't just a catchy phrase. It was the product of decades of math, sweat, and one very patient man staring at a computer that looked like a refrigerator. Pop culture might have simplified it, exaggerated it, and turned it into time travel movie plots. But behind all the jokes and metaphors lies something profound. The reminder that the world is sensitive, delicate, and endlessly unpredictable. And honestly, isn't it comforting to think that even the tiniest flutter might matter? If there's one place where humans love chaos more than anywhere else, it's the casino. Bright lights, free drinks, no windows, and absolutely no clocks. Casinos are basically temples built to worship unpredictability. And sitting at the heart of it all, games of chance. Dice, cards, roulette wheels, slot machines, machines designed to flirt with chaos. But here's the twist. Gambling didn't just entertain people, it accidentally helped invent entire branches of mathematics. Without dice games, we might not even have probability theory. So in a way, every time someone lost their rent money at the craps table, math gained a new theorem. Let's start in the 1600s with two famous names, Blaise Pascal and Pierre de Fermat. These guys weren't hanging out in smoky casinos in Las Vegas. They were corresponding by letter, debating questions sent to them by gamblers in France. People wanted to know things like, if a dice game is interrupted halfway through, how should the pot be fairly divided? Pascal and Fermat worked it out, and in the process they basically invented probability theory. So yes, the math that now powers everything from insurance companies to artificial intelligence began with people arguing about dice money. Humanity at its finest. Casinos took full advantage of this. Roulette wheels, for example, look like they're random. The little ball spins, it bounces, and everyone holds their breath. But in theory, it's not random. It's deterministic chaos. If you knew the exact velocity of the ball, the spin of the wheel, the tiny imperfections in the metal, You could calculate exactly where it will land. The problem is, those little differences snowball so fast that in practice it feels unpredictable. That didn't stop people from trying. In the 1970s, a group of students at the University of California built a secret computer they could hide in their shoes. Using tiny switches, they tapped their toes to input the wheel's speed, and the computer gave them predictions. For a while it worked. They actually beat the roulette wheel. Casinos freaked out, but eventually chaos caught up. Tiny errors made the predictions fail, and the students went back to being broke. Still, it's a great story. Blackjack card counters may have gotten movies, but the roulette shoe computer people? Legends. And then there's the stock market, which is basically a giant casino where the dice are disguised as investments. Economists used to think markets followed neat patterns like a bell curve. Prices would rise and fall in predictable ways. But then Benoit Mandelbrot came along, the fractal guy, and ruined the party. He showed that markets were way more chaotic than people wanted to admit. Prices swing wildly, fractal patterns show up everywhere, and crashes happen far more often than the neat bell curve suggests. This drove economists nuts, but traders loved it. Suddenly, fractals and chaos theory became tools to understand risk. Not perfectly, nothing in finance is perfect, but enough to explain why markets sometimes behave like stampeding herds instead of polite calculators. And gambling isn't just money games. Chaos sneaks into sports betting, lotteries, even video games. Ever opened a loot box in a game and gotten trash instead of the cool item you wanted? Congratulations, you've just participated in a billion-dollar chaos industry. But here's the funny thing. Humans are terrible at understanding probability. Our brains hate randomness. We're wired to see patterns even when they don't exist. That's why gamblers fall for the gambler's fallacy. If a roulette wheel lands on red 5 times in a row, people convince themselves that black is due. Nope, each spin is independent. Chaos doesn't care about your feelings. Casinos know this, of course. They're built on it. The house doesn't beat you by predicting dice rolls or roulette outcomes. It wins because the odds are slightly tilted in its favor. Over time, chaos always leans toward the casino, and the flashing lights and free drinks are just there to keep you rolling the dice long enough for math to do its job. But let's zoom out. Gambling didn't just inspire probability. It also showed scientists how chaos works in real life. Throwing dice is a chaotic system. Roulette is a chaotic system. Stock markets are chaotic systems. All of them follow rules, but small variations make them unpredictable in practice. They're like little laboratories where humans study chaos without realizing it. There's even a weird beauty in it. Picture a roulette wheel spinning under golden lights, the ball clattering and bouncing unpredictably, the crowd leaning forward in suspense. That's chaos theory on display, packaged as entertainment. It's math disguised as adrenaline. And sometimes chaos even gives the underdog a chance. The unpredictability of games means anyone could win big, even if the house usually wins. That slim possibility is what keeps people hooked. It's irrational, but it's also deeply human. We don't love certainty, we love hope. We love the idea that maybe, just maybe, tonight's the night chaos will land in our favor. Of course, most of the time it doesn't. Casinos don't run on luck, they run on math, and math always wins in the end. But in the middle, in that moment where dice roll and wheels spin, chaos feels alive. It feels like anything is possible. And that's why gambling fits so perfectly into the story of chaos theory. It's not just about losing money, it's about learning humility. It's about realizing that even when you know the odds, the outcome is still unpredictable. And it's about admitting that deep down we kind of like it that way. So the next time you walk past a slot machine, or watch a dice roll across a table, or check the stock market and wonder why your retirement account looks like a roller coaster, remember, you're gambling with chaos, and chaos always plays for keeps. When most people hear the word chaos, they picture pure randomness. Dice flying across a table, a room full of toddlers with crayons, my desk on a Monday morning. In other words, mess with no structure at all. But chaos theory isn't about pure mess. It's about the surprising fact that even in disorder, there's hidden order lurking underneath. Let's go back to Lorenz and his butterfly. Remember how his weather simulations spun out into unpredictable paths. At first glance, it looked like the system was just wandering around like a drunk raccoon in the night. But when he plotted the data in 3 dimensions, something magical happened. The points didn't scatter everywhere, they formed a shape, the Lorenz attractor. That butterfly wing pattern wasn't random at all, it was order hiding in the mess. This is the heart of chaos theory, deterministic chaos. The systems aren't random, they follow exact rules. Newton's laws still apply, the equations are crystal clear, but because they're so sensitive to initial conditions, the outcomes look unpredictable. Zoom in close, and it's disorder. Zoom out, and you see patterns. Think of it like waves on the beach. Stand with your toes in the sand and try to guess the timing of the next wave. Good luck. They seem completely unpredictable. But step back and watch for a while and you realize there's a rhythm. Tides rise and fall with the moon. Storms create swells. Beneath the choppy surface, order hides in the water's chaos. Another great example is turbulence. Airplanes hate turbulence, passengers fear it, and scientists, well, they obsess over it. Turbulence looks like pure randomness, a wild scramble of eddies and currents, but underneath it's governed by equations. Extremely complicated ones, yes, but still equations. And when you simulate turbulence, fractal patterns emerge. Even in the bumpiest ride, there's geometry. It's the same with fractals in nature. Coastlines, clouds, trees, they look messy, but zoom in and you see repeating structures. They're chaotic, but not random. That's the magic distinction. Chaos isn't nonsense. It's structured unpredictability. This order in the disorder idea fascinated mathematicians like Mitchell Feigenbaum. He studied how simple systems transition into chaos, and he found universal constants hidden in the madness. Imagine tweaking the growth rate of a rabbit population. At first, the system stabilizes. One generation follows the next. Increase the rate a little, and it starts oscillating between 2 values. Increase it more, and it flips to 4, then 8, then 16, doubling and doubling until bam, chaos. But here's the kicker. The exact points where the system flips follow a precise mathematical ratio, no matter what system you use. Rabbits, dripping faucets, chemical reactions, the same ratio appears. That's not randomness. That's order peeking through the cracks. It's like chaos has its own secret code. And this secret code shows up everywhere. Stock markets, brain activity, ecosystems, they all bounce around unpredictably, but within certain limits. You can't say exactly what will happen tomorrow, but you can map out the boundaries of possibility. That's what strange attractors do. They don't give you a script, but they give you the shape of the story. Here's a fun way to picture it. Imagine a pinball machine. The ball bounces unpredictably from bumper to bumper. You could never calculate its exact path, but you know it won't leave the machine. It stays inside the boundaries. That's chaos theory in a nutshell. Unpredictable paths inside predictable limits. And there's something oddly comforting about that, because it means the universe isn't just random nonsense. It's not dice rolling in the dark forever. It's structured, it's patterned, it's meaningful, even when it feels messy. Of course, people ran wild with this idea. Philosophers and poets loved it. Suddenly, chaos theory wasn't just about weather or math, it was about life. They said things like, see, even in the chaos of human existence there's hidden order, which sounds deep, but also kind of obvious if you've ever cleaned your room and realized everything had a place under the mess. But the metaphor does work. Our lives feel unpredictable. We make small choices that ripple out. Unexpected events knock us sideways. But zoom out and you see patterns, habits, relationships, cycles of history. There's chaos, but it's not lawless. We all live inside strange attractors, whether we realize it or not. Even science itself thrives on this tension. Total order would be boring. If everything were predictable, there'd be nothing left to discover. Total randomness would be useless. No patterns to study, no rules to uncover. Chaos sits right in the middle, giving us surprises but also clues, disorder wrapped in order. One of my favourite descriptions comes from mathematician James Blake, who wrote the book Chaos. He said chaos is order masquerading as randomness, and that's exactly it. When you look at a chaotic system long enough, you start to see the masquerade. Beneath the wild mask, there's structure smiling at you. So the next time life feels chaotic, traffic jams, weather forecasts, stock markets, or just your daily schedule, remember it's not pure randomness. There's hidden order, patterns, attractors, fractals. The mess has meaning. You just need to zoom out far enough to see it. Because even when math refuses to give you neat answers, it still whispers a promise. Chaos may be unpredictable, but it's never without design. If chaos theory has taught us anything, it's that the line between order and disorder is thin, paper thin, razor blade thin, and for engineers, pilots, and anyone building machines that need to not explode, that line is everything. Welcome to the edge of control. Let's start with airplanes. Most people think planes fly because of engines. Engines help, sure, but the real magic is air moving smoothly over wings. As long as the airflow behaves, the plane behaves. But sometimes, the airflow doesn't behave. It separates, it swirls, it becomes turbulent. That's chaos creeping in, and when it happens, the plane shakes, passengers grip their armrests, and the pilot calmly says, "Just a little turbulence," which is pilot code for the atmosphere is throwing a tantrum, and we're along for the ride. Airplanes live on the edge of chaos. Too much control, and they stall. Too little, and they spin. Engineers spend decades designing systems that balance perfectly between the two. A jet fighter, for example, is actually unstable by design. It's deliberately chaotic, twitchy, hard to fly unless you add a computer that constantly nudges it back into line. That's why fighter pilots look so cool. They're literally surfing chaos with the help of a machine that makes thousands of adjustments every second. Rockets? Even worse. Rockets are basically giant tubes of chaos strapped together with math and prayer. They wobble, they vibrate, they try very hard to flip upside down and explode. Keeping one on course requires constant correction, like walking a drunk giraffe down a tightrope. And even then, small errors can cascade into disaster. Remember the early space race? Rockets blew up a lot. Chaos was always waiting, just one decimal point away. But it's not just things that fly. Bridges can dance on the edge of chaos too. In 1940, engineers built the Tacoma Narrows Bridge in Washington state. It was sleek, elegant, beautiful, and then the wind hit it. The bridge started twisting, waving, buckling, like it was auditioning for a heavy metal music video. Eventually, it tore itself apart in spectacular fashion, all because of chaos in aerodynamics. The lesson? You can't bully nature into submission. Design has to respect the edge. Even something as ordinary as cars deal with chaos. Think about self-driving vehicles. They're supposed to keep everything safe and smooth, but the world they drive in is chaotic. Pedestrians, potholes, cyclists, squirrels with no respect for traffic laws. A self-driving car has to constantly calculate, adjust, and react to tiny changes. One delay, one bad assumption, and you get chaos on wheels. That's why building a reliable self-driving system is so hard. The math of chaos is baked into every intersection. And then there's electricity. The power grid looks stable most of the time. You flip a switch, the lights turn on, no problem. But the grid is actually a delicate balance of supply and demand. If demand spikes too quickly, or if one power station goes down unexpectedly, the whole thing can cascade into blackouts. That's chaos at work, a small disruption rippling into massive effects. Engineers fight chaos daily just to keep your Netflix running. But here's the strange part. Living on the edge of chaos isn't always bad. Sometimes it's the sweet spot. Complex systems often work best right at that boundary between total order and total disorder. Too much order, and a system gets rigid, brittle, unable to adapt. Too much chaos, and it falls apart. But balance the two, and you get flexibility, creativity, resilience. Biologists call this the edge of chaos. Ecosystems thrive when they're dynamic but not collapsing. Brains work best when neurons fire with a mix of stability and unpredictability. Even evolution itself runs on this balance. If life were perfectly ordered, it would never change. If it were pure chaos, it would never survive. The edge is where the magic happens. Humans instinctively know this too. Think about sports. A game that's too predictable is boring. A game that's total chaos is unwatchable. The best matches happen on the edge when order and chaos collide, when outcomes are uncertain but not random. That's why we love underdog victories, last-minute goals and buzzer beaters. It's chaos, but controlled chaos. Or music. A song that's too rigid is dull. A song that's pure noise is unbearable. But put a little improvisation on top of structure. Jazz, rock solos, freestyle rap. And suddenly it's alive. That's the edge of chaos again. Even our daily lives hover there. Too much routine and we get bored. Too much unpredictability and we get stressed. The sweet spot is somewhere in between. Enough stability to feel safe, enough chaos to keep things interesting. It's why we plan vacations but leave room for surprises, why we set goals but also chase opportunities. We live best at the edge. Of course, staying there isn't easy. Systems can tip into disorder fast. Airplanes crash, bridges collapse, markets tumble, ecosystems fail. That's why engineers, scientists, and frankly, all of us are constantly nudging things back into balance. It's exhausting, but it's also what makes life dynamic. Chaos theory teaches us that control is never absolute. It's a dance. Push too hard, and you break it. Let go completely, and you lose it. The art is in balancing, flying right at the edge without tipping over. So next time you're sitting on a bumpy airplane, or stuck in a traffic jam, or watching a game that has you on the edge of your seat, remember, this is the edge of chaos. And maybe, just maybe, that's exactly where we're supposed to be. When you think of chaos theory, you probably picture storms, fractals, maybe a roulette wheel. But here's the twist. Chaos isn't just out there in nature or in casinos, it's inside you. Right now, your body is basically a walking chaos laboratory, and that's a good thing, most of the time. Let's start with the heart. You might think a healthy heartbeat is perfectly steady, like a metronome, tick-tock, tick-tock. But if your heart actually beat like that, you'd be in trouble. A real healthy heart has tiny irregularities in its rhythm. Those little fluctuations are what keep it adaptable. They allow your heart to speed up when you run, slow down when you rest, and respond to stress. But here's where chaos sneaks in. If the rhythm becomes too irregular, you get arrhythmia. The beat turns chaotic in the dangerous sense, fluttering, fibrillating, losing its structure. Suddenly the thing that keeps you alive becomes unpredictable in a way you definitely don't want. Doctors now use chaos theory to study heart rhythms, looking for patterns in the irregularity to predict when things might tip from healthy adaptability into dangerous chaos. In other words, a butterfly in your chest can really ruin your day. And it's not just the heart. Your brain is a chaos machine too. Neurons fire in wild, complex patterns. It's not random, it's structured chaos. That's what gives you thought, creativity, memory. A perfectly orderly brain would be boring, robotic. A totally chaotic brain would be noise. The sweet spot, the edge of chaos, is where intelligence happens. But when the balance tips, things can go wrong. Epileptic seizures, for example, are bursts of chaotic firing in the brain. Too much synchrony, too much feedback, and suddenly the whole network goes into overload. Scientists studying epilepsy often use chaos models to understand why brains sometimes spiral out of control. Even sleep has chaos hiding inside it. Your brain waves don't just click neatly from one state to another. They drift, fluctuate, wobble between patterns. Dreams themselves, fragmented, unpredictable, surreal, might be chaos theory at work inside your head. If you've ever dreamed about something bizarre like eating spaghetti with a walrus while flying a kite, that might just be your neurons surfing chaos. Let's move deeper. Your immune system. It's not a neat little army that marches in perfect rows. It's a chaotic swarm. Antibodies, white blood cells, signaling chemicals. They bounce around, interact, and create unpredictable dynamics. Sometimes the chaos works perfectly, knocking out infections. Other times it misfires and you end up with allergies or autoimmune disorders. Again, chaos lives right under your skin. Even digestion has its own flavor of chaos. The gut is full of microbes, trillions of bacteria all jostling and competing. It's an ecosystem as complex as a rainforest. And it behaves the same way. Tiny changes in diet or environment can ripple out unpredictably. Eat one suspicious taco and suddenly the entire system reorganizes itself in ways you'd rather not describe. That's chaos in action. Then there's movement. Walking looks simple, but it's actually a chaotic system. Muscles, joints, nerves, all coordinating in a feedback loop that constantly adjusts. That's why robots struggle so much to walk like humans. It's not just mechanics, it's chaos management. One tiny misstep, one pebble on the sidewalk, and the system has to adapt instantly or you faceplant. Sports push this to the limit. Think about basketball. 10 players, 1 ball, constantly shifting strategies, tiny movements changing everything. That's why predicting the outcome of a game is nearly impossible. It's not just talent, it's chaotic dynamics in action. Your body, your brain, the team, the crowd, all swirling together in a storm of unpredictability. And let's not forget emotions. Ever had a day where one small thing like spilling coffee set off a chain reaction of frustration that derailed everything? That's basically a butterfly effect in your mood. Emotions are chaotic systems bouncing between calm, stressed, happy, annoyed. Psychologists sometimes model mood swings using chaos equations. Your brain is basically a Lorenz attractor with feelings. The funny thing is, chaos in the body isn't just a problem. It's also a strength. Too much order in a system makes it rigid, unable to adapt. Too much chaos makes it collapse. The balance between the two, the edge of chaos, is where life thrives. That's why doctors now study healthy variability. A heart with no variability is sick. A brain with no fluctuations is broken. Chaos in the right dose keeps us alive. And here's the big philosophical twist. We are chaos. Every thought, every heartbeat, every breath is a chaotic process balanced on a knife's edge. We like to think of ourselves as orderly beings, but the truth is, we're walking strange attractors. Our bodies are fractal, our brains are non-linear, our moods are unpredictable. We're butterflies wearing human skin. Scientists are still unraveling all this. Chaos models are used in cardiology, neurology, psychiatry. Even cancer research has dabbled in chaos theory, studying how cells tip from orderly growth into uncontrolled spread. The hope is that by understanding the hidden order in these chaotic processes, we can predict when things will go wrong and maybe stop it before it happens. But beyond medicine, there's something oddly comforting about knowing chaos runs through us. It means we're not machines, we're not metronomes, we're not predictable scripts. We're alive, dynamic, messy, surprising. Our bodies carry the same patterns as galaxies, storms, and fractals. So the next time your heart skips a beat, or your thoughts race in weird directions, or you find yourself laughing and crying at the same time, remember, it's not failure, it's chaos, doing its thing. It's the same butterfly that stirs storms, fluttering inside you. And maybe that's the most beautiful part of all. When most people hear the word chaos, they think of disaster. Hurricanes tearing through towns, traffic jams stretching for miles, that one drawer in your kitchen filled with batteries, scissors, and 3 different kinds of tape that somehow never work. Chaos has a bad reputation, but here's the secret mathematicians discovered. Chaos can be beautiful. Let's start with the visuals. Strange attractors, fractals, turbulence, all the patterns chaos produces are stunning. When Lorenz first plotted his butterfly-shaped attractor, he wasn't trying to make art. He just wanted to understand weather. But when those loops appeared, scientists didn't just see equations, they saw elegance. Infinite swirls, delicate lines, never repeating, never boring. Chaos had drawn a masterpiece. Then Benoit Mandelbrot came along with his fractals. The Mandelbrot set isn't just math, it's practically a psychedelic painting. Zoom in, and the same spirals and lightning bolts repeat endlessly. Artists jumped on it immediately. Fractals became album covers, posters, screensavers. Even today, you can buy prints of the Mandelbrot set to hang on your wall. Think about that, math equations hanging next to your living room couch, masquerading as decoration. But it's not just in labs and posters. Chaos creates beauty everywhere in nature. Look at a tree. No 2 branches are identical, but together they form a harmonious pattern. Look at clouds, endlessly shifting but always recognizable. Look at lightning zigzagging across the sky, or river deltas winding like veins across the land. These shapes aren't neat circles or triangles. They're chaotic, jagged, self-similar, and that's what makes them beautiful. There's even a name for this kind of beauty: fractal aesthetics. Psychologists have found that people actually prefer fractal patterns. Show someone a picture of random scribbles and a picture of fractals, and most will gravitate toward the fractals. Our brains like the balance between complexity and structure. Too simple, and we get bored. Too random, and we get confused. Fractals sit in the sweet spot, the edge of chaos. Artists have known this instinctively for centuries. Think about Jackson Pollock. At first glance, his drip paintings look like pure mess. But scientists analysed them and discovered fractal patterns hidden inside. Pollock wasn't just splattering randomly. His movements created structures that echoed natural chaos. Maybe that's why people find his work oddly mesmerizing. It resonates with the same patterns our brains see in nature. And it's not just painting. Architecture too has embraced chaos. Gothic cathedrals with their branching arches and stained glass windows are basically human-made fractals. Modern architects use fractal geometry to design buildings that feel organic, like they grew instead of being built. Even music plays with chaos. Jazz improvisation, Indian ragas, electronic loops, they all balance repetition with unpredictability. Too much order and the song is dull. Too much chaos and it's noise. The magic lives in between. Nature, of course, doesn't care about aesthetics. It doesn't create fractals to look pretty on your bedroom wall, but we can't help finding them beautiful anyway. Snowflakes, seashells, coastlines, they remind us that beauty doesn't need to be symmetrical or simple. It can be jagged, infinite, chaotic. And here's the funny twist. Chaos can even be therapeutic. Doctors have found that looking at fractals reduces stress. Patients recovering in hospitals with views of trees, natural fractals, heal faster than those staring at concrete. People who spend time in forests or by the ocean often report feeling calmer, more balanced. Chaos, it turns out, is good for your mental health. Who knew the secret to relaxation was staring at broccoli? Even technology has borrowed chaos's beauty. Computer graphics use fractal algorithms to generate realistic landscapes in movies and video games. Every mountain, every cloud, every alien planet you've seen on screen owes its realism to chaos math. Instead of designing each rock and tree by hand, animators let fractal equations do the work. Hollywood owes a lot to Lorenz's butterfly. But the strange beauty of chaos isn't just visual, it's philosophical too. There's something comforting about knowing the universe isn't sterile, predictable clockwork, that small changes can ripple out, creating surprises. It makes the world feel alive, unfinished, capable of wonder. Think about it. If everything were perfectly predictable, sunsets would lose their magic. You'd know exactly how each one would look, down to the shade of orange. Boring. But because of chaos, tiny shifts in clouds, humidity, dust, the sky surprises us every night with new colors. That's chaos painting the horizon. Or take music again. A live performance always has a little chaos. Timing variations, improvisations, the unexpected energy of the crowd. That unpredictability is what makes it electric. A perfectly programmed machine could play the same notes flawlessly, but it wouldn't feel alive. Beauty hides in the imperfections. Even our relationships are chaotic. One random meeting, one accidental conversation, one butterfly wing flap, and suddenly your life changes forever. It's unpredictable, yes, but it's also what makes human connections feel magical. The beauty of chaos is that it keeps life open-ended. Scientists surprisingly agree. They talk about chaos as a source of creativity. Systems at the edge of chaos, brains, ecosystems, societies are the ones that adapt, innovate and evolve. Too rigid and they stagnate, too wild and they collapse. Balance them just right and they flourish. That balance produces not just survival, but beauty. So maybe chaos isn't the villain we thought it was. Maybe it's the artist of the universe, sketching jagged coastlines, painting turbulent skies, composing improvisational symphonies. Next time you're mesmerized by waves crashing on the shore, or lightning splitting the night sky, or even just the mesmerizing swirl of cream in your coffee, remember, you're witnessing the strange beauty of chaos. And maybe, just maybe, that butterfly flapping its wings isn't trying to start a storm. Maybe it's just adding one more brushstroke to the universe's masterpiece. By now, we've spent a lot of time with this butterfly. We've watched it flap in Brazil, stir tornadoes in Texas, inspire Hollywood movies, and sneak into math textbooks. But here's the big question. What does the butterfly really mean? Because deep down, chaos theory isn't just about weather models or pretty fractals. It's about something far more unsettling and fascinating. How we understand the universe and maybe even ourselves. Let's rewind to the old worldview. For centuries, science believed in determinism. Newton's laws made it feel like the cosmos was a giant machine. Give it an initial push and you could calculate everything forever. Pierre-Simon Laplace even imagined a being, Laplace's demon, that could know every particle's position and momentum. With that knowledge, the demon could predict the entire past and future of the universe. Comforting, right? Everything neat and tidy. Then along comes Lorenz's butterfly and ruins the demon's day. Because chaos theory says, nope, Even if the rules are deterministic, the tiniest uncertainty in the starting conditions grows until prediction collapses. You don't need randomness to break certainty. You just need sensitivity. The butterfly is proof that Laplace's dream of perfect prediction was just that, a dream. And this shakes things up way beyond meteorology. If the weather can't be perfectly predicted, what about economies? What about ecosystems? What about your life? Suddenly, the universe isn't a clock, it's jazz improv. The butterfly is a reminder that the future isn't carved in stone, it's carved in jello, wobbly, delicate, and one good nudge away from a completely new shape. Philosophers love this stuff. The butterfly effect gets dragged into conversations about free will, destiny, and fate. If small actions ripple out into giant consequences, does that mean we're in control of our lives or not at all? On one hand, the butterfly says, your choices matter. Even the smallest decision can reshape the future. On the other hand, it says, you'll never know how. The ripples are unpredictable. It's both empowering and humbling at the same time. It also forces us to rethink responsibility. Ever held a door open for someone and wondered if that tiny kindness set off a chain of good events? Or maybe you've snapped at someone in traffic and thought about the ripples of that bad mood. Chaos theory doesn't say these ripples definitely change the world. It says they could, which is both a little terrifying and strangely poetic. And let's not forget philosophy's favorite rabbit hole, determinism versus randomness. The butterfly lives right between them. Chaos isn't random, it's deterministic equations all the way down, but it feels random because prediction breaks down. That middle ground is unsettling. We're not trapped in destiny, but we're not free of structure either. We're butterflies flying through a storm of rules we can't fully see. Religion and spirituality have also borrowed the metaphor. Some see the butterfly effect as proof of interconnectedness, that every action, no matter how small, touches the web of existence. Others see it as a symbol of fragility, a reminder of humility. Even if you don't buy the math, the image is irresistible. The universe, vast and chaotic, trembling from the flap of a wing. But maybe the most important meaning of the butterfly is this. It humbles us. For centuries, humans thought we could master everything with enough data and enough equations. Chaos theory reminds us that control has limits. The butterfly says, you're not the boss of the universe. You're part of it. Sensitive, fragile, unpredictable, just like the systems you're trying to control. And honestly, that's not bad news. Imagine if everything was predictable, if life unfolded like a script, step by step, no surprises, you'd know exactly how every day would go. Sure, you'd never get caught in the rain without an umbrella, but you'd also never stumble into unexpected joy. No surprise friendships, no chance encounters, no weird little accidents that change everything. Chaos, and the butterfly at its heart, is what makes life worth living. Think about your own story, trace it back. How many small events shaped who you are? Maybe one random teacher inspired you. Maybe one chance meeting changed your career. Maybe you were born in one city instead of another, and everything after unfolded differently. That's the butterfly at work. Tiny flaps, massive consequences. Even science itself is full of butterfly moments. Lorenz only discovered chaos because he rounded numbers differently one afternoon. If he'd typed 6 decimals instead of 3, he might never have noticed. Chaos theory could have stayed hidden for decades longer. A single flap of a butterfly wing in Lorenz's lab, and math history changed. So what the butterfly really means is this. The universe is delicate. Small things matter, not in a cheesy self-help way, but in a deep, mathematical, unignorable way. The butterfly is a reminder that we live in a world where certainty is an illusion, where tiny differences can rewrite the future, where unpredictability is baked into the rules of reality. And maybe that's the best metaphor of all, because every day, in every choice, we're butterflies. We don't know which wing flap will stir a storm or a breeze, but we know they all ripple out somewhere. The butterfly isn't a warning or a threat or even just a scientific metaphor. It's a symbol, a whisper from the universe that says, you are small, but you matter. You are fragile, but you make waves. You live in chaos, but there is beauty in that chaos. And honestly, that's a meaning worth holding on to. By now, we've spent a lot of time with this butterfly. We've watched it flap in Brazil, stir tornadoes in Texas, inspire Hollywood movies, and sneak into math textbooks. But here's the big question. What does the butterfly really mean? Because deep down, chaos theory isn't just about weather models or pretty fractals. It's about something far more unsettling and fascinating: how we understand the universe, and maybe even ourselves. Let's rewind to the old worldview. For centuries, science believed in determinism. Newton's laws made it feel like the cosmos was a giant machine. Give it an initial push and you could calculate everything forever. Pierre-Simon Laplace even imagined a being, Laplace's demon, that could know every particle's position and momentum. With that knowledge, the demon could predict the entire past and future of the universe. Comforting, right? Everything neat and tidy. Then along comes Lorenz's butterfly and ruins the demon's day. Because chaos theory says, nope, even if the rules are deterministic, the tiniest uncertainty in the starting conditions grows until prediction collapses. You don't need randomness to break certainty, you just need sensitivity. The butterfly is proof that Laplace's dream of perfect prediction was just that, a dream. And this shakes things up way beyond meteorology. If the weather can't be perfectly predicted, what about economies? What about ecosystems? What about your life? Suddenly the universe isn't a clock, it's jazz improv. The butterfly is a reminder that the future isn't carved in stone, it's carved in jello, wobbly, delicate, and one good nudge away from a completely new shape. Philosophers love this stuff. The butterfly effect gets dragged into conversations about free will, destiny, and fate. If small actions ripple out into giant consequences, does that mean we're in control of our lives or not at all? On one hand, the butterfly says, your choices matter. Even the smallest decision can reshape the future. On the other hand, it says, you'll never know how. The ripples are unpredictable. It's both empowering and humbling at the same time. It also forces us to rethink responsibility. Ever held a door open for someone and wondered if that tiny kindness set off a chain of good events? Or maybe you've snapped at someone in traffic and thought about the ripples of that bad mood. Chaos theory doesn't say these ripples definitely change the world. It says they could, which is both a little terrifying and strangely poetic. And let's not forget philosophy's favourite rabbit hole, determinism versus randomness. The butterfly lives right between them. Chaos isn't random, it's deterministic equations all the way down, but it feels random because prediction breaks down. That middle ground is unsettling. We're not trapped in destiny, but we're not free of structure either. We're butterflies flying through a storm of rules we can't fully see. Religion and spirituality have also borrowed the metaphor. Some see the butterfly effect as proof of interconnectedness, that every action, no matter how small, touches the web of existence. Others see it as a symbol of fragility, a reminder of humility. Even if you don't buy the math, the image is irresistible. The universe, vast and chaotic, trembling from the flap of a wing. But maybe the most important meaning of the butterfly is this: it humbles us. For centuries, humans thought we could master everything with enough data and enough equations. Chaos theory reminds us that control has limits. The butterfly says, you're not the boss of the universe, you're part of it. Sensitive, fragile, unpredictable, just like the systems you're trying to control. And honestly, that's not bad news. Imagine if everything was predictable, if life unfolded like a script, step by step, no surprises. You'd know exactly how every day would go. Sure, you'd never get caught in the rain without an umbrella, but you'd also never stumble into unexpected joy, no surprise friendships, no chance encounters, no weird little accidents that change everything. Chaos and the butterfly at its heart is what makes life worth living. Think about your own story. Trace it back. How many small events shaped who you are? Maybe one random teacher inspired you. Maybe one chance meeting changed your career. Maybe you were born in one city instead of another, and everything after unfolded differently. That's the butterfly at work. Tiny flaps, massive consequences. Even science itself is full of butterfly moments. Lorenz only discovered chaos because he rounded numbers differently one afternoon. If he'd typed 6 decimals instead of 3, he might never have noticed. Chaos theory could have stayed hidden for decades longer. A single flap of a butterfly wing in Lorenz's lab, and math history changed. So what the butterfly really means is this: the universe is delicate. Small things matter, not in a cheesy self-help way, but in a deep, mathematical, unignorable way. The butterfly is a reminder that we live in a world where certainty is an illusion, where tiny differences can rewrite the future, where unpredictability is baked into the rules of reality. And maybe that's the best metaphor of all, because every day, in every choice, we're butterflies. We don't know which wing flap will stir a storm or a breeze, but we know they all ripple out somewhere. The butterfly isn't a warning, or a threat, or even just a scientific metaphor. It's a symbol, a whisper from the universe that says, you are small, but you matter. You are fragile, but you make waves. You live in chaos, but there is beauty in that chaos. And honestly, that's a meaning worth holding on to. So here we are, at the end of our long journey through chaos. We've chased butterflies through weather labs, gambling halls, forests, fractals, rocket ships, and even the human body. We've seen math throw tantrums, scientists go slightly mad, and nature show off its wildest tricks. And after all this, the butterfly is still here, quiet, delicate, and whispering something we've almost been too busy to hear. What does it say? Maybe it says, the universe is not what you thought. It isn't a neat clock ticking predictably. It isn't pure randomness either. It's something in between. Rules with surprises, structure with wiggle room, a dance that never quite repeats itself. The butterfly's whisper is the reminder that certainty is an illusion, and unpredictability is part of the design. Think about how strange that is. The equations governing chaos are completely deterministic. Newton's laws still apply. Energy is conserved, forces add up, math does its job, and yet the outcomes slip through our fingers. The whisper says, you are not in control, not completely. You can measure, model, and simulate all you want, but the future will always keep some secrets. At first, that sounds scary. Nobody likes the idea that tomorrow could spin off in directions we can't predict. But listen closely, and the whisper isn't frightening. It's freeing. If the world were perfectly predictable, there'd be no surprises, no chance encounters, no accidental discoveries. Chaos is what lets life stay alive. The whisper also says small things matter. A tiny flap, a rounding error, a missed bus, a single conversation, these can ripple out and change everything. You may never know which flap matters most, but you know that every flap has the potential. That's humbling, but it's also hopeful. You don't need to move mountains to shape the future. Sometimes you just need to move air. It also tells us something about beauty. We like to think beauty is symmetry, simplicity, order, but chaos shows us another kind of beauty. Jagged coastlines, turbulent skies, infinite fractals, improvisational jazz. Beauty that isn't neat but endless. Beauty that comes from unpredictability. The butterfly whispers, don't fear the mess, it's where wonder lives. And maybe most importantly, the whisper reminds us of humility. For centuries, humans believed we could master everything, predict every orbit, every storm, every future. Laplane's demon was our imaginary mascot of certainty, but the butterfly ruined that. And in doing so, it gave us a gift, humility in the face of the universe. Knowing that we don't, and can't know it all, is not defeat, it's wisdom. It keeps us curious, keeps us searching, keeps us listening. Here's the funny part. The butterfly doesn't need us to notice it. It's been flapping its wings long before Lorenz gave it a metaphor, long before Mandelbrot drew his fractals, long before we built our clunky computers. But by noticing it, by listening to its whisper, we've learnt something essential about the nature of reality. We've learnt that chaos isn't just destruction, it's creation. It's not just unpredictability, it's possibility. Think about your own life for a moment. Trace back the chain of events that brought you here, listening to this story. How many small flaps shaped your path? A teacher who said the right words, a chance meeting, a decision to click on one video instead of another. That's chaos theory woven into your story. The butterfly doesn't just flap in Brazil, it flaps in your living room, in your relationships, in your dreams. And what does that mean for tomorrow? It means you don't need certainty to keep moving. You don't need a perfect forecast to live a meaningful life. You just need to listen to the whisper, embrace unpredictability, respect the small things, and trust that the mess has meaning, even if you can't see it yet. In the end, chaos theory isn't about scaring us with tornadoes or confusing us with equations. It's about reminding us that the world is alive, it's dynamic, surprising, endlessly unfolding, and the butterfly, fragile and quiet, is its messenger. So tonight, as you drift off to sleep, picture those delicate wings. Picture them stirring the air, creating ripples that spread across the world, not to terrify you, Not to overwhelm you, but to remind you, the universe is not predictable, it's not controllable, but it is beautiful, and you are part of its endless dance. The butterfly's whisper is simple, life is chaotic, and that's what makes it wonderful.